In this video, we're going to be looking at the concept of Newton's laws of motion. What are we going to do? We're going to take an in-depth look at each of Newton's three laws of motion. We're going to see how all three laws are connected to one another. We'll also define the term equilibrium and look at problem-solving strategies for problems dealing with forces. Why are we doing this? Because Newton's three laws of motion describe all forms of translational motion. That also includes vibrational motion, as well as circular motion. But it only is easily done if you truly understand what the laws are. Newton's laws of motion are often oversimplified when they're first taught, which leads to many misconceptions and confusions when we're at our level here. So they need to be reviewed and explained in detail. Also, all of our translational motion equations, even again those for vibrational motion, as well as circular motion, can be originated back to Newton's laws of motion. And when we're dealing with very advanced systems where there are no pre-established motion equations like the ones that we use, we need to derive new equations, and we often start from Newton's laws of motion. That is not something that we're going to deal with a lot at our level, since that often requires calculus. However, this is the skill set that leads to that ability. Also, to make accurate predictions on how an object or system will behave, you need to really understand what these laws are and what they mean. So you need to understand the relationship, how forces affect an object's motion. If you just have an equation memorized, you can't really do this. Also, many aspects of business, government, personal behavior, society, and culture mirrors the properties of Newton's laws. They're not the same thing. However, there are parallels, and developing the insight and critical thinking skills related to Newton's laws strengthens those related skills and insights that are key for understanding those social, financial, and cultural applications. Now, when looking at Newton's first law of motion, this lays down the foundation for all the other laws of motion. And it simply says that the motion, which is the speed and direction, or the lack of motion that an object has or a system, does not change unless there is a net unbalanced external force acting on it. In short, nothing about the motion is going to change unless something from the outside forces it to change. And not having motion is having motion. Now, the second law is just a mathematical application to this. What if I have an external force? How does the motion change? That's what this is talking about. If there is no net unbalanced force acting on the object or system, then the acceleration is zero. That's kind of obvious, because if we just look at the equation, net force equals ma, if my net force is zero, the acceleration must be zero. And that's exactly what this statement here is saying in the first law, where if there is no outside force, then the motion of the object does not change. Now, if there is an external force that's non-zero, which means it's unbalanced, then there is an acceleration. And that acceleration is going to be equal to the net force trying to create the change divided by the inertial mass of the object. Now, why does this equation work? Well, forces try to create the change. Objects resist a change in motion. That goes right back to the first law. Mass is the resistance to that change. So we have the mathematical equation that was found through experimentation, net force equals ma. Actually, the equation was originally that your acceleration was your net force divided by your mass, but we often write it as net force equals ma for a single object. If I have a system, then it's the net force on the system equals the total mass of this system times the acceleration of the system. Please notice these equations are almost exactly the same, and if I have only one object, then my object is my system, and these equations are exactly the same. The third law relates to how I resist the change in motion. Think about it. Uh, I'm standing here by myself. Somebody else comes along. I'm not moving. They decide to push me to get me to move. According to the first law of motion, I don't want to move. So what am I going to do if you exert a force on me? Well, the first thing is, if there's nothing to stop me from having my motion changed, it will change. And my mass is going to resist that change and minimize the acceleration. But then, how do I resist? What do I do? That's where the third law comes in. The third law explains how I resist. Whenever you exert a force on me, so whenever one object or system, we'll call it A, tries to exert a force on another object or system B to change its motion, then B, the object or system that's being affected by A, resists by exerting a force back onto A with the same amount of force but in the opposite direction. So the net force between A and B in their interaction just between each other is zero. There still needs to be an external force on the system for there to be a change in motion for the system. However, these two forces between A and B have to always cancel out because the reaction is the attempt to resist change in motion. We can kind of think of it this way. Newton's first law of motion is the one true rule that we have for motion. Nothing's going to change unless something from the outside forces there to be a change. The second law is just a mathematical application to that first law. Okay, so if I am going to be forced to change, how do I change? At what rate do I change? How much do you need to exert on me to get a desired change? All of that is addressed through this equation. So this is nothing more than a mathematical consequence or application of the first rule. The third law explains the consequence. If you try to change me, I'm going to change you back. That's exactly what the third law is about. So again, all these laws are interconnected. They're all extensions of the first law of motion. We can also think of Newton's three laws from a perspective issue. The first law of motion, the only true rule that we have, is a very global perspective. This applies to both objects and systems. An object's motion will not change unless there's an external influence to make it change, just like a system's overall motion will not change unless there's an external influence on the system. If there is no external force on a system, individual objects inside the system can have their individual motions change, but the change of one object must cancel out the change in another object, so as a whole, there is no change in the system's motion. However, if there is an external force, then that can always change for the entire group as well as the individuals. Now, the second law of motion only works from an object perspective. If we have a system, we will always end up simplifying it down into a single object. That's because Newton's second law deals with only external forces. Only the net external force is equal to the mass of an object times the acceleration, or the net force on the system is equal to the total mass of the system times the acceleration of the system. But let's be honest, if I'm combining all the masses of the individuals up into the system, I've simplified the system into a simple object. The second law of motion has no consideration, no concern, and doesn't even recognize the existence of internal forces. That's because I have taken something that is complicated and simplified it to a simple object. And objects don't have interiors. So if I want to understand anything about the interior of a system, I never look at the second law of motion because it ignores the interior completely. If I choose to view something purely as a system, the third law of motion does come in very handily at that time. That's because the third law of motion can only explain systems and not objects. The third law of motion deals with the interaction between two things. A pushes on B, so B pushes back on A as a reaction. However, if I combine this up into just A plus B, then these forces cancel out and they're totally ignored. If I have just A cannot exert a force on anything. Thus, even if it was to somehow try and exert some sort of force, there's nothing to push on, nothing pushes back on A, and A cannot exert a force on itself. Nothing can. That's why it always has to be an external influence from someone else. So the third law only works from a system perspective. Now, while it is true that any system can be viewed purely as a system, many systems are way too complicated to work easily from a purely system perspective, which is why we'll always simplify the system to an object first. Please notice that in any real situation where you want in-depth understanding, both the second law and third law fail individually. This gives you a good starting point overall trend of a group, but fails to give you any detail about what's going on inside. The third law will give you all this detail about the interior, but it is such a convoluted and complex point of view that it's very hard to get started and very difficult to work for most people. Only by combining these two rules up do you really get to have a very powerful methodology for finding out what's going on. But when these two rules meet up, they actually go right back to the first law of motion. So all three laws aren't just connected or related, they are really the same idea, each from a different perspective of how the situation can be viewed. Newton's first law of translational motion is purely conceptual in its nature. And because of that, people often kind of just bypass that to focus on the second law, which is very mathematical. And that's always a mistake because the second and third laws are both rooted from the first law. If you cannot understand the first law, then the actual application of the second and third laws will often run you astray. Not only that, but a lot of times when you are needing to predict what's going to happen, the correct answer comes from understanding an insight rather than an actual mathematical equation. Not only that, but again, Newton's first law of translational motion applies to all cases of translational motion. We're talking single objects, we're talking systems of objects, we're talking with systems within systems moving. We are talking about straight line motion, projectile motion, circular motion, even again vibrations. Anything that's not rotational. And even when it comes to rotational motion, there are going to be similarities to Newton's laws for rotational motion. They are not exactly the same, but again, there will be similarities. And if I have an understanding of one thing, then it's much easier for me to understand the similarities of something that is different. So we're going to take a look at several different scenarios dealing with the first law of motion. And the first one is actually a fairly classic scenario where we have a person in a car. The person is not wearing their seatbelt. The car is moving at a constant velocity until it hits a wall. Then all of a sudden, it looks like the person is thrown from the car. I want to focus on that term thrown from the car? And is that really what's happening? And I want to point that out because that's what you often hear. Someone wasn't wearing their seatbelt and they got thrown through the windshield. And is that really the case? So let's take a look first at the question, what is the reason that the car stops? And that's pretty easy. There's a wall that's in the way. The car is moving, everything is good. We have forces acting on the car initially if the car is moving at a constant velocity. We have the force of gravity going down on the car, the force of the road pushing up. Nothing else is acting on the car, and so it moves at a constant velocity. Then all of a sudden it hits a wall, and it pushes the wall forward. So all of a sudden there's a force on the wall that we'll call force on wall from car. Now, that wall is incredibly massive because it's rooted into the earth. So your tracks are trying to move the entire earth, if you want to think about it, when you hit this wall, because they're physically attached. Now, according to the third law of motion, if I exert a force on something, that something exerts a force back on me, equal in magnitude and opposite in direction. So because the car exerts a force on the wall returns a force onto the car. So we're going to call this force on car from wall. These two forces are equal in magnitude and opposite in direction. But the mass of the car is much smaller than the mass of the wall Earth system. Thus, the acceleration of the car will be far more noticeable than the wall that's bolted and attached to the earth. So the car, from our perspective, stops quickly, actually. In fact, it gets thrown backwards. So it makes perfect sense that the car's motion changes. But then we have the person who was, quote unquote, thrown from the car. Now, if I throw a ball, I exert a force on that ball to make it move forward. Does the person experience a force throwing them forward? Well, from the car's perspective, sure. Look, you're in my seat, and all of a sudden you're out of my seat and you're flying through over my hood and you're moving forward away from me. Clearly something must have thrown you, something must have ejected you from my car because I'm still here, I'm still the car. But the reality is, what reason does the person have to stop? The wall exerted a force on the car, not the person. The person had motion. And unless there is a net unbalanced external force acting on this person, that motion will not change. While they're in the car, there is a balance of forces. We have the force of gravity pulling down on the person and the force of the seat pushing upward. There's no other forces acting on that person. When the car stops moving, for whatever reason, the person has no reason to stop. And since they have no reason to stop, they're not going to stop. And so they keep moving forward. Now, once they leave the car, they do have an acceleration of gravity pulling downward because this force is now gone. And so they will accelerate and they will travel as a projectile because there is a reason for their motion to change. There's an external force that's unbalanced on that individual. But the truth is, the seatbelt doesn't prevent you from being thrown from the car. It prevents you from leaving the car when the car's motion changes and yours doesn't. The seatbelt provides a reason for you to stop moving because now when the car stops and you lunge forward, not lunging, you're continuing your motion forward because the seat stopped. The seatbelt is in your way. You now have to push the seatbelt out of your way. And if the seatbelt is bolted to the car, you're now trying to push the car forward, and the car will now push you back, keeping you in place. Here we have a case of a little kid that's on a sled, and there's a dog who's very excited. He's going to pull the sled, and The dog runs, and you can actually see this happy dog just pull the sled. And the sled moves. So the question that we have here is, what's the reason is there for the dog to move? And I don't mean who's ever calling the dog whatever. What force causes the dog to move forward? And if you take a look at the dog's legs, they push the ground backward. So there we have a force on ground from dog. Now, the dog is actually unknowingly trying to alter the rotation of the earth. I'm exerting a force here as the dog across the earth's surface, kind of like a person's hand on the side of a basketball that's balanced on a single finger, and I get the ball to spin. Here the dog is trying to change the rotation of the earth. However, the earth being far more massive will be less affected by this force than the dog would be by the reaction force of the ground pushing the dog forward. All right, so if the dog pushes the earth one way, the earth is going to push the dog the other. So we have force on dog from earth. That's why the dog moves forward, because there's an external force acting on this dog that's unbalanced. We do have the force of gravity pulling down on the dog. We do have the force of the ground pushing up on the dog. They cancel out. But we have this net external force acting on the dog, which we often call as friction. Now, why does the sled move? Well, if you take a look, there is a cord that's attached to the dog. So when the dog runs forward, he exerts a force on the cord. And the cord is attached to the sled. And if you notice, that cord gets rather tense. The reason for that is the sled is at rest and it wants to remain at rest. The dog has to exert a fair amount of force on that sled to get it to move. And that's why we see this tension in the wire there, because that is the building up of the force that's causing the sled to move forward. Now, is there a friction force from the snow on the sled? Absolutely, but it's probably very small, definitely smaller than what the dog can exert, and so the sled moves forward. But now let's talk about the kid. What's pushing the kid forward? The dog isn't pulling the kid. The dog is pulling the string, and the string is pulling the sled. Nothing's pulling the kid. So the kid who's at rest wants to stay at rest, whether he realizes it or not. And so when the dog pulls the sled, there's no reason for the kid really to move. Now, there is a force of friction between the sled and the kid, which is why you see the kid rotate backwards, because that friction force creates a torque on the kid's bottom while there's nothing on the top causing the kid to rotate. And there's just not enough time for that force to actually make the kid move forward. The dog bolts off way too quickly. Now, if the dog had moved very slowly, the force would have more time to act on the kid and would actually be smaller too, and the kid would probably stay on the sled. But the bottom line is there's no reason for this kid to move. Just like there is no reason for this person to stop moving, there's no reason for this kid to move. There's no external force that's going to push the kid forward. We do have external forces on the kid pushing downward because of gravity, and upward, which is the force of the sled, but nothing forward. So if you're telling the kid you should move, the kid's response is, why should I? If you're telling this guy, hey, you should stop, why should I? Another great example of this actually is when we take a look at events that happen very quickly in photos that show the process in a very slow rate. So here we have a car that's going to pierce water balloons, and we can see that the balloons collapse very rapidly, and we now get to see what the water looks like. Normally we just see a gush of water. It happens too fast for our brains to process. So here we can actually see what's going on. Now, the first question I have is, what's the reason for the released water to fall? If you notice, while we have the water balloons, nothing's falling. All of a sudden, you pop the balloon and the waters do start to fall. And the answer for that's really easy. Gravity. There's no reason for the water to fall while it's in the balloon because we have the force of gravity going down and the force of the balloon, whatever it's attached to at the very top, holding it up. But when you pierce the balloon, that top force is gone, leaving only the force of gravity. We have an unbalanced force, and so the water has a reason to fall. More importantly, though, when the water falls, the shape of the water doesn't change. It's in whatever shape it was before the balloon popped, and now it keeps that shape as it falls. Again, this happens so fast, we don't see this, but it's just like one giant water droplet from the rain. And the question really isn't why does the, I'm sorry, the question really isn't why doesn't the water change its shape as it falls? The real question is, why should it? Every piece of the water experiences a force of gravity going down. Every piece of water will fall at the same acceleration due to gravity because they're all in free fall. But if there's no external forces other than gravity, then they're all going to fall at the same rate. So whatever shape they have in the beginning will actually be the shape they have at the end. There is no reason for the shape to change. Here we have the case of a girl who is holding on to the sides of a playground ride. We have this boy who's spinning it, and the girl moves in a circle. And we ask the question, what is the reason for the girl moving in a circle? And that's again because she's holding on. As she holds on to the side, there is a force that's pulling her into the center of the circle. If she lets go, what happens? Well, if she lets go at this moment, she flies off in a straight line. And that's because her inertia tells her to move in a straight line. The only reason she is changing direction is because there's an external force of the ride. We call that the centripetal force. Now, as far as the ride is concerned, it thinks the girl is pulling the ride out. That's the reaction force that the girl's body exerts on the ride for trying to pull her in. The ride pulls her in, her body pulls the ride out. That outward force is that centripetal, centrifugal force that people talk about. So again, the ride exerts an inward force on the girl. That's the centripetal force. The girl's body, through Newton's third law, reacts by pulling the ride out. That's the reaction force on the ride, not the girl. And that's the centrifugal force that people often like to think about. But the girl does not experience a centrifugal force. She only experiences a centripetal force. And again, those are terminologies that people often get confused. One of the reasons being because they sound so similar, centrifugal, or centripetal. But the bottom line is the girl's inertia is going to make her go forward. That's why we see her legs swing out, because her body is trying to move in the direction that's presently moving in as the ride pulls her inward. And when she lets go, she doesn't fly out, she flies forward, because there's no reason for her to fly out. Nothing's pulling her outward. A classic or standard term that you will often hear in areas such as chemistry, biology, physics, even sometimes in terms of politics or finances, is something known as equilibrium. Many people misunderstand what equilibrium is. Some people think equilibrium is a point where nothing is happening. It's a point where everything is balanced or equal, since it is in fact the term equilibrium. They think it's equal, but that's not exactly true. Equilibrium is a
balance point where the state of a system as a whole seems not to change, but that doesn't mean that nothing is happening. So for example, if we take a look at biology, there's a thing known as genetic equilibrium. This is a point where the frequency of a particular property in a species is consistent. And so here we have a bunch of butterflies where we can see that half of them are red and half of them are blue. Now, over a prolonged period of time with breeding of the butterflies, we see the same proportions as before. So in the beginning with these butterflies, we have half blue, half red. And now several generations later, we still have half blue, half red. So if we're looking at this particular property, we could just turn around and say, nothing has happened. Now that's not necessarily true. These butterflies, for example, have all died. They have bred and crossbred with the other butterflies. It just so happens that the number of red butterflies that's been created have been offset by the number of reds that have been lost. And the same thing with the blues. And so there is a balance here in the proportions, although there is things that are taking place. In chemistry, there are often two kinds of equilibrium that you guys talk about. We have our equilibrium in a chemical reaction where you have your reactants that engage with each other and they make a product. But this could be a reversible process where the product breaks back down into the reactants. If we reach a equilibrium with this reaction going to the product and vice versa, then the quantity of reactants remains the same, just like the quantity of products remain the same. The proportions do not change. But that doesn't mean the process stops. As we can see here, it's like we have these reactants here that are being moved over by this ant to the products. But as that's happening, this ant is carrying products over to the reactants, breaking it down. We do in fact have a constant flow back and forth, but since they are balanced out, we can just pretend that nothing is happening because it's not affecting the final outcome of the quantities of the products or the reactants. If we take a look at heat flow, we have something called thermal equilibrium. This is when I have two objects that are at different temperatures, and when they come in contact, they become the same temperature. And we often overhear the oversimplification that heat flows from hot to cold, and that is true, but heat also flows from cold to hot. But more heat flows from hot to cold. It flows at a higher rate from hot to cold than it does from cold to hot. So when these two things touch A and B, there's a whole lot of heat flowing one way and a little bit of heat the other way. As these temperatures become closer together, the heat flows become closer together. And when I reach thermal equilibrium, the heat flows are the same. Heat still flows from one to the other, but just equal quantities. So neither one is going to heat up or cool down, because whatever one gains is also losing simultaneously. So there is no net change in the amount of thermal energy that they have. This doesn't seem to be very important, except for the fact that when something else gets introduced into the system that then throws the equilibrium off, all of a sudden we see these dramatic changes. People get confused with this because if nothing's happening, why did something change? And it's not that nothing was happening. There was a balance of power. If we think about this in terms of military strength, we have two countries that aren't necessarily friends. They have equal military might, so they're not at war with each other, because if I engage war with this other country, I could be destroyed. I could lose. We have a balance of power. So we have a point of peace. but that doesn't mean that we're friends. It doesn't mean that there isn't a potential for conflict. It just means that whatever I have, you can balance out with, and so we have equilibrium. Now, with the development of a new weapon or technology, if that throws the balance of power off, equilibrium is broken, and all of a sudden we see a very different behavior that takes place. That's what we can see here. When we add something else to the system that disrupts the equilibrium, we see a shift then in the amount of product or reactants. We see a shift in the temperature of who's gaining or who's losing. We see a shift in the frequency or distribution of various genetic traits or properties or species. When dealing with physics or engineering, equilibrium is going to be referring to when all the forces balance out on an object, so the net external force on an object or system is zero. For us, dealing with physics, it means there's no change in velocity. It means automatically there is no acceleration. And this is what we're dealing with here. Equilibrium does not mean forces are equal. Equilibrium does not mean that there are no forces. Equilibrium just simply means that whatever some sets of forces are trying to do to an object, other sets of forces are canceling out, so there is a balance of the forces. If something disrupts this balance, there will be a broken equilibrium and there will be an acceleration. Newton's first law of motion often is referred to with equilibrium. An object at rest tends to stay at rest. An object in motion tends to stay in motion with no acceleration. No change in velocity, no change in speed, no change in direction, which means no acceleration, unless there's a net external unbalanced force acting on them. So if we focus on just the first part of that, where I'm at rest and I stay at rest, or my velocity, speed, and direction remain constant, that's under the condition that I am in a state of equilibrium, that there is no net unbalanced force acting on me. That's what equilibrium means for us, that the net external force is equal to 0 newtons. So if I have something, let's say like a sign that is just simply hanging, we'll have multiple forces here. We'll have the force of gravity pulling straight down, because gravity can only pull down, and my strings are actually at an angle. Neither one of my tensions has to equal the force of gravity, but their combination in the upward direction must cancel out gravity. See, each tension force will be broken up into two components. I'll have a force tension Y and a force tension X. For this guy, the tension Y pulls up, tension X pulls to the left. For this guy, I have a tension Y going to the top and an Fx, force tension X, going to the right. These two forces have got to cancel out if this sign is going to remain at rest. Likewise, the two tensions upward combined must equal the force of gravity going down. So these guys must equal out with this guy. If they are off balance, this sign will accelerate either to the right or to the left, up or down, or some combination of up and down with right and left. And that's because the forces are off balance. As long as these forces remain balanced, then I am in a state of equilibrium and the sign's motion does not change. And since it has no motion to begin with, it doesn't change. It stays at rest. However, equilibrium does not mean at rest. Most people think this is the only state of equilibrium, and it is not. It is just one of the many cases. The second case is the in motion with no change in speed nor direction. So cases of a person sliding on ice at a constant velocity is in fact a point of equilibrium. Here we have our player moving at a constant velocity. They do not change their speed. They do not change their direction. We do have forces acting on them. We have the force of the ice pushing upward, the force of gravity going down. My velocity is going in this direction. And since these two forces cancel out, and there are no other forces at all on the system, there's no reason for this velocity to change. Likewise, if I have an object that is falling, it could fall in a state of equilibrium if it falls at a constant velocity. We often call that, again, a terminal velocity. This is a point on where their velocity has reached the final velocity the fall will allow. Terminal just simply means ending, last. So this is the ending velocity, the last velocity they will have. As the cat falls through the air drag builds up. Initially, it's next to zero, and it slowly builds up, becoming stronger and stronger. As long as the air drag force is less than gravity, the cat accelerates downward. But the moment the air drag force equals the force of gravity, the cat stops accelerating. The cat's velocity is downward. But if these two forces are equal, then there is no reason for this velocity to change. Don't get me wrong, this could end very poorly for the cat unless the cat's parachute opens up. Once that happens, it is going to throw this equilibrium off, and this air drag force becomes very big in the beginning, causing the cat then to slow down dramatically. As the cat slows down, the air drag force will become smaller again until eventually the air drag force equals the force of gravity, and the cat will fall again at a constant velocity. It'll be a smaller velocity than before because for a little bit the equilibrium was thrown off. When looking to solve problems of single objects in equilibrium, we can often solve these problems through a four-step process. In fact, most of our force problems, regardless of their scenario, will be solved in a four-step process, all pretty much the same with only minor tweakings along the way to adjust for the individual needs of the situation. The first step, no matter the situation, is always to draw a free body diagram. This is often the simplest thing for people to overlook, thinking it's such a simple thing to do, you don't really need it, and trust me, this is something that you need. This here is the most important step, and it's also perhaps the hardest one to get correct. That is because the free body diagram requires critical thinking. You're going to draw out all the forces acting on and in the system. If it is just an object, it'll be only the forces acting on the object, since the object has no interior, so there would be no internal forces. Later on, when we look at systems, you'd be drawing both the external forces acting on the system as well as the internal forces acting inside the system. This is a key thing that we need because we need to have a visual that keeps track of all of our forces so we can correctly write out a force equation. Without the free body diagram, everything else falls apart. This diagram is unique to the situation. So you have to think of all the forces that are involved, the ones that are stated and the ones that are not stated but are always present. If you have any forces at an angle with whatever your XY axes are set up to be, then you need to break those vectors up into their X and Y components. Once you break those vectors up into X and Y components, redraw the free body diagram one more time. You're not going to have the vectors that you've broken down. Instead, you'll replace those individual forces with the components that you drew instead. This will make your life a whole lot easier. So if I had a force of gravity going downward and one force at an angle, then my first diagram would be the force of gravity going down and that other force at an angle. But then when I do step 1B, I'll take that one force at an angle, break it up to the X and Y components, and have a diagram now with three forces. The force of gravity going down, the X component of the force I broke up, and the y component of that force that I broke up. And then I can move on to my next step. Working with components is often much easier than dealing with forces at an angle. So this is always the best thing to do. Always rewrite the free body diagram. People who do not, and they just break forces up into components, often get their equations wrong because they try to reincorporate the other original force that they broke up. Keep your diagrams neat, keep them simple, and you'll have a very easy time with these types of problems. The next step is simply to write out the net force equation. Now this is Newton's second law, net external force equals ma, and you're set. If you're dealing with a force system that's along only one axis, then you can do the x or the y, whichever is appropriate. If you're dealing with a two-dimensional problem, you have to write the force equation twice. Once for the x-axis, once for the y-axis. The net external force really is going to be just the summation of all the forces. So the summation of Fx is really the forces to the right plus the forces to the left. Keep in mind, one of these has to be negative. By convention, right is positive, left is negative. But you can be unconventional if you choose to. It doesn't matter. But you must be consistent. Likewise, with the y-axis, by convention, up is positive, down is negative. And you can switch that if you choose to. Again, as long as you are consistent. How can I tell if a force is supposed to be positive or negative? I'm going to refer back to my free body diagram. What forces am I using? This all stems from this diagram. If I do not have a good free body diagram that's correctly drawn out, I cannot write out this force equation. And people often ask me before I even look at the problem, what's the force equation? And my answer is always the same. I don't know. Until I draw a free body diagram and look at the forces, I don't know what I'm going to do. I don't know what the equation is. Once I have that visual, it is so easy to solve, but I need that first. The third step is to set my acceleration equal to 0 meters per second squared. I know it's 0 meters per second squared because I'm in a state of equilibrium. There's the thing. If I'm in equilibrium, then the acceleration must be 0 meters per second squared. If it is not in equilibrium, then this statement isn't true. So anytime I'm dealing with equilibrium, I don't have to solve for acceleration. I know it. It is 0. That means my net force is automatically 0. Net force equals ma. And if a is 0, then the net force must equal 0. So now I have two equations, one for the x-axis and one for the y-axis, that I can now easily use to solve for any force. So I'm going to just simply solve the problem. That's my fourth step. If I am dealing with Newton's second law, this is where all of a sudden I have that imbalance of forces. Now the second law becomes very significant and highly applicable. I can now turn around and use that to find the acceleration of my system. The car hits the wall and the wall creates an imbalance force on the car. All of a sudden this force appears. I can now find the acceleration of the car by taking that unbalanced force and divide it by the mass of the car. These two things have canceled out. In fact, so that makes this pretty easy to work with. I don't have to include the person's mass because the person's isn't changing their motion, so they don't count. As long as that person is moving on their own, separate of the car, I do not need to include their mass. Had the person worn a seat belt, and then the wall would have to stop the car as well as the person, I would have to then include the person's mass. But since they did not wear a seat belt and they are leaving the car through their own inertia, the wall isn't stopping them. Thus, I do not include the person's mass in this equation. If I have an object that is falling freely, which means there's no air resistance, it's free fall, then we know the only force acting on that system is the force of gravity. And we have my free body diagrams right here where I see only the force of gravity. I can now say that the acceleration of the ball is equal to the force of gravity acting on the ball divided by the mass of that ball. And for the feather, the acceleration of the feather is equal to the force of gravity on the feather divided by the mass of the feather. And again, this helps explain why the acceleration of the ball and feathers are the same. Because even though the force of gravity on the ball is much larger than the even though the force of gravity on the ball is much greater than the force of gravity on the feather, suggesting the ball should fall faster, the ball also has more mass than the feather, has more resistance to the force than the feather. That mass is trying to slow down what the acceleration is. So we have a natural balance here. And so all objects fall at the same rate. If I am not in free fall, if there is in fact air resistance, then we have an additional force acting on the ball and the feather. And this throws off that balance for acceleration. Now the less massive object could potentially fall faster. Oh, sorry, the less massive object could actually fall slower because of the effects of air resistance. The less massive object could also fall faster, depending on how aerodynamic that object is compared to the heavier object. If I drop a small rock and a large elephant, it is possible for the rock to hit first because of the amount of air resistance acting on the elephant, especially if the elephant is wearing a parachute.
Newton's second law of translational motion also deals with objects that move in a circle, not just objects that move in a straight line or projectiles. For example, if we have a satellite orbiting the Earth, we know that the net overall force acting on that satellite, really the only force acting on that satellite between the Earth and satellite, would be the force of gravity from the Earth acting on the satellite. If we take a look at the free body diagram of the satellite and compare it to that of the falling ball and feather in a vacuum, we see that the free body diagrams are the same. We might have a arch drawing to show the motion of the satellite, but when we look at the forces themselves, we see that the forces are exactly the same. This means the behavior of the motion of these objects is pretty much going to be the same. And the truth is, a satellite is nothing more than a falling object in free fall. The only difference is it outruns the surface because it falls down as it moves to the side, while for a traditional falling object such as the ball and feather, the velocity is along the same axis as the force. But we can find the acceleration of all these objects through Newton's second law, where the force of gravity acting on the object divided by the mass of that object is in fact the acceleration caused by gravity. And just like the acceleration of the ball and feather, the acceleration of the satellite really will be independent of the mass of the satellite, for the very simple reason the acceleration due to gravity is independent of the mass of the objects that are falling. When we need to solve problems dealing with Newton's second law of motion, we're going to use a problem-solving tactic that is very similar to what we did with equilibrium. The reason for that is because the process that we're using is not so much a formulaic process that works for a specific circumstance, but is rather a process of thinking that is far more global and universal. So we're going to see a lot of commonalities. We're going to focus specifically right now on situations of a single object and later on we'll take a look at a system of objects, where again the process will be almost exactly the same, with only one or two minor tweakings to how we approach our diagrams, in all honesty, just to better simplify the situation. But the thinking process, even then, will be exactly the same. So just like in equilibrium, my very first step is going to give me a visual of what is going on. So I'm going to draw a free body diagram where I'm going to have all the forces acting on this object. If necessary, I will take forces that are at an angle with my XY axes and break them up into components. Again, for the same reason with equilibrium, it will just make my math easier to work with. It is very important that if I break vectors up into components, I redraw that free body diagram one more time with those components and not those original forces that were broken down. So for example, if I had a block that experienced only two forces, the force of gravity and a force at an angle, then I would redraw my free body diagram as the force of gravity going down that was not broken into components. But then I'd have Fx and Fy instead of the original force that I had. I do not want to draw my original force on this diagram. If I do, it is easily misinterpreted as having four forces acting on this diagram, but there are really only two forces, or if I prefer, one force and two components, but I don't have four forces. People who draw all of their forces and components onto one diagram because they think it's going to be easier often get gummed up for the very simple reason there are way too many forces acting on this, and the diagram no longer represents what is really happening. So redraw the diagram a second time. It will only make your life a whole lot easier. Once I have my free body diagram drawn out and complete, I am ready to do the second step, which, like before with equilibrium, is to simply write out the net force equations. If I'm dealing with only one axis, I will write out the equation only one time. If I'm dealing with both axes, I'll write it twice, once for the x-axis, once for the x-axis, once for the y-axis. Again, forces are vectors, so I have to be consistent with the signs that I use. By convention, right is positive, up is positive, left is negative, down is negative. But I am more than welcome to switch these if I choose to. I can easily say right is negative and left is positive, up is negative and down is positive, if I choose to. And there might be some circumstances where I might think that is more appropriate. But keep in mind, you must always be consistent with everything. Accelerations are also vectors. So if the right is positive for my forces, then for accelerations, right is positive as well. So if I have an acceleration to the left, I must call that a negative acceleration. That's also true for positions as well as velocities. Once I have set up my equations, I can now get ready to solve the problem. Now, when I was looking at equilibrium, I would just set the acceleration equal to 0 because acceleration is 0 in equilibrium. Equilibrium means that there is no change in motion, thus there is no acceleration. The net force must be 0. In cases that are not equilibrium, then there must be an acceleration and the net force is not 0. This is unique for each situation, so I can't automatically just apply a number. I will have to know what it is, be told what it is, or solve for it. Now, some cases, they will give you the acceleration directly in the text of the question. If so, great, run with it. Do be careful of your signs. Often they will not tell you whether the sign is positive or negative directly. They'll simply state the direction of the acceleration, and you must infer what that sign is. Do make sure that you're consistent with the points of view that you've established for what direction is positive, what direction is negative. And several problems you'll be asked in the end to solve for something about the motion itself, such as a position, a velocity, the time it takes for a change. And so we will be giving you all of the forces acting on the object as well as the mass, which means you can easily use the force equations to find the acceleration if you're given all the forces as well as the mass. However, in some circumstances, we will not be asking about something about the motion, but instead we'll be asking for what the mass of the object is or one of the forces acting on that object. In that type of scenario, we will be giving you information about the motion, the initial and final positions, the time it took for that to happen, the change in velocities, the time it took to happen, the initial and final velocities, as well as the displacement. In any of those circumstances, you'll have to find the acceleration not through the force equations, because you'll be missing something, such as the mass or the forces, but instead you'll have to use the kinematic motion equations, or the motion equations for circular motion. So if we are given the text information without a graph, you will have to use the kinematic equations or centrifugal motion equations to find acceleration. If you are given a graph, such as a velocity versus time graph or position versus time graph, you can either use the kinematic equations to solve those graphs, or you can use whatever property of the graph you know of to find the acceleration. Admittedly, most people rather just use the kinematic equations, since that is rooted from those properties. And the kinematic equations are always provided. Once you have the acceleration, you can now solve the problem. Unless the problem was, what's the acceleration, you're going to have to solve for something else, such as what is the mass of the object, knowing the forces, or what's a force, knowing the mass and the acceleration, or find me the velocity at a given time, the distance traveled or displacement at a given time, anything like that based off of the acceleration. This is similar in a way to projectile motion, but you had to find the time before you solve for anything else. Here it's going to be very similar. We have to find acceleration before we look for what we're really being asked to solve for. Here we have a sample problem where I have a 10-kilogram box that's going to be lifted from rest to a speed of 20 meters per second in 5 seconds. And I want to find the lifting force on the box. Please notice the very first step is a free body diagram. People who do not draw out a free body diagram often get this question wrong because they forget about the force of gravity. We have gravity pulling down on the box, and at an acceleration of negative 9.8 meters per second squared, the force of gravity is negative 98 newtons. I also have a lifting force that I do not know. My diagram isn't complicated, it's just these two forces, but it does lay down the foundation that I need. And I'll be honest, most of our free body diagrams are not going to be complicated, but they are still incredibly important to draw out. Now I do step 2. The net force equals ma. The net force is the lifting force upwards plus the negative 98 Newton force because it's going down. So force lift plus negative 98 equals 10 AY, because I'm dealing with the y-axis. I would love to solve right away for the lifting force, but I can't because I do not know the acceleration, so I need to solve for that, which leads to step 3. I was given the initial and final velocities of the block, as well as the time it took for the velocity to change. This yields the velocity formula. So I'm going to use the velocity formula to solve for the acceleration. And I find that it's positive 4 meters per second because I know the final velocity was positive since it was lifted, meaning it's moving upward. This acceleration sign is incredibly important. Please make sure that you include it, because if this box was being lowered, then that acceleration would be negative, and it takes a lot less force to lower something than it does to lift it. So please make sure you include that sign. Now that I have the acceleration, I will simply plug it into the equation I had in step 2, which leads me now to step 4, where I can now just simply solve for the lifting force. My net force is positive 40 newtons, since 10 times positive 4 is positive 40, meaning that the lifting force has to be positive 138 newtons, which means the lifting force is pulling upwards. I know that because it's a positive sign. Please notice that the lifting force is greater than the force of gravity because I want the object to accelerate upwards. I don't want to just balance gravity. I want to overcome it and cause an object to speed up in the upward direction rather than to accelerate in the downward direction or speed up in the downward direction. Newton's third law only deals with the internal forces of a system. So we will never talk about an object and the third law. I need multiple objects involved, each one interacting with the other to create a system. The third law only deals with internal forces. As a single object, I have no interaction with myself. There would be no internal forces. The third law clearly states that whatever force object A exerts on B, B exerts the exact amount of force in the opposite direction. And that does sound simple enough, especially when dealing with cases such as the Earth orbiting the Sun. We can turn around and picture the Sun's pull on the Earth and the Earth pulling back on the Sun, and we can go, well, obviously they'll be equal and opposite. That just makes sense. People often get gummed up, though, when we have multiple objects, 3 or more in a system. And the reason for that is the fact that people often start to oversimplify scenarios and not think about who is really pulling on whom. So for example, here I have what's called an Atwood machine where I have 2 blocks attached to each other by way of a string, and the string is over a pulley. Now the question is, what does M2 pull on? Well, obviously, since M1 is going up, or M is moving up, M2 is pulling on M. But that's not exactly true. M2 is not attached to M. M2 is attached to a rope. So M2 is actually pulling on the rope. And what's the rope pulling on? Well, that must be M. But that also is not exactly true. The rope on this side is actually the rope on the side of 2M is actually connected to a pulley. And it's actually pulling that side of the pulley downward, causing the pulley to rotate. So the M2 is really pulling on the pulley. So the pulley pulls back on M2. Since the pulley is trying to rotate in this direction, the pulley must also then try and lift M2 up. So this pulley, by way of the string, is actually pulling on M, and M is pulling back on the pulley. So when we really think of this scenario deeply, M2 is not pulling on M, but actually it's pulling on the pulley. The pulley is pulling on both objects, and both objects are pulling on the pulley. Now, one of the reasons for people getting confused on this is when we first start off looking at these systems, we want to keep things really simple for everyone. So we pretend the pulley has no inertia. We pretend it has no mass. So we pretend the pulley doesn't exist. Now, if there's no pulley here, or it plays no role, then M2 must be pulling on M and vice versa. But the moment we make this a real scenario, things get complicated fast for people because they've never looked at this deeply. So M2 only pulls on the pulley. M only pulls on the pulley. And again, they really just pull on the rope that's pulling on the pulley. M1 and M2 really don't pull on each other at all with the pulley in between. Now the question is, does the pulley matter? That's going to be something that we decide as we look through the problems. If we're told it's a massless pulley or an ideal pulley, it doesn't matter. And we can just pretend these two forces are equal. However, if it's a real pulley, which you will see 100% in the actual real world that we live in, we'll actually have to accommodate for this, which is easily done. You accommodate by just being honest and write down what is actually happening, not oversimplifying. But we get into that aspect later on in the course. Newton's third law stipulates that the forces between the objects are equal, but that does not mean that their accelerations are going to be equal. Here we have the Earth orbiting the sun, and if you notice, the sun really doesn't seem to move. The Earth moves in a circular or elliptical path around the sun. We can definitely notice the motion of the Earth, but we really don't notice much of the sun. The reason for that is, according to Newton's second law of motion, the net force acting on an object is equal to the mass times acceleration. This means that the net force on the sun must equal the mass of the sun itself times the sun's acceleration, while the net force on the Earth must equal the mass of the Earth times the Earth's acceleration. These two values must be equal and opposite in direction. However, since the sun has a much larger mass, its acceleration will be much smaller than the Earth's, so we don't see such a rotation. If we see a cannon firing a cannonball, again, the ball and cannon feel the same amount of force exerted from each other, but the cannon, having less mass, accelerates much more, moving a much greater distance. This is why internal forces never change the location of the center of mass of a system. Here we have the center of mass of a system of a cannonball and cannon before it's fired. After we fire the system, the cannonball fires a much larger distance forward than the cannon moves backwards, but because the cannonball has much less mass than the cannon itself, the center of mass of the system does not actually move.
If we look at the math behind the cannon firing the cannonball, we can start off with our center of mass equation, where the total mass of the system, which is the cannon and the ball, times the center of mass of the system itself, is equal to the summation of the individual masses times their individual locations. So we start off with saying the mass of the cannon plus the cannonball itself summed up times the center of mass, which we will set to be a position of 0 as the origin, must equal, in the end, the mass of the cannon times its final location plus the mass of the cannonball times its final location. This is because internal forces do not affect the location or the motion of the center of mass of the system as a whole. Well, if that's the case, then there must be a ratio between the centers, there must be a ratio between the displacement of the cannon and that of the ball. And we can easily see that the mass of the cannon times the location of the cannon is equal and opposite to the product of the mass of the ball times the location of the ball. So we can easily turn around and say then that the displacement of the cannon itself, or its final position from 0, is actually equal to the final location of the ball itself times a ratio of m ball over m cannon. And then we have a negative sign that comes over as well, which means the location of the cannon must be opposite in direction of the ball itself, and that if the cannon was 5 times more massive, the cannon would have traveled 1/5 that displacement, because it has 1/5 the mass, because it has 5 times the mass of the cannonball. It has 5 times the inertia. It carries 5 times the weight in the overall system location. If we apply that to Newton's third law of motion, we can turn around and say that the cannon, when firing the ball, the cannon exerts a force on the ball that would be in the forward direction or left to my screen, and then the ball exerts the equal amount of force in the opposite direction on the cannon. Well, if we are ignoring any other forces, particularly along the x-axis, then the net force on the cannon must equal the net force on the ball in magnitude and opposite in sign. This means that the mass of the ball times the acceleration of the ball being fired must equal the negative mass of the cannon times the acceleration of the cannon. Again, we can set up a very similar equation to what we have here, where in the end, the acceleration of the cannon would be the negative of the ball times the ratio of the mass of the ball over the mass of the cannon. So that means if the cannon was 5 times more massive than the cannonball, the acceleration during the firing would be 1/5 that of the ball, which makes sense because with 5 times the mass, I have 1/5. With 5 times the mass, I have 5 times the inertial resistance to the forces pushing on me. So I'd have 1/5 the acceleration. And since I have 1/5 the acceleration, I would definitely not speed up as much nor travel as far either. So we see a linking between center of mass and Newton's third law. All right, that's going to wrap us up here. Hopefully this is starting to make some sense. If you're watching this video and you're going, I have a good handle on this, then you are very well prepared and you're ahead of the game for when we meet up. If you watch this video and you go, I kind of get it, but I really wish I had some help, that's exactly where you need to be, because we are going to go over this in class and get that practice in. And as always, if you're looking at this going, I am totally lost, that's totally okay. This is stuff that you really need to have down in the next coming month, so we have time to work on these larger skills. We just have to work on the foundations right now. And as always, these videos are not to get me out of actually teaching, so we'll go over any questions that you have in class.